we talked about rotational kinematics, which is describing things that are in motion, that are rotating. And we use three terms primarily: this angular displacement, angular velocity, and angular acceleration. And all of these three are very similar to the terms that we learned in linear kinematics. And there's appropriate analogies when we move over to rotational dynamics and explaining why things rotate that translate very easily from linear dynamics. So our main question is, why do things rotate? What causes them to rotate? And to try and unpack this question, we're going to look at a wrench. So what would cause this bolt to rotate? First, we're going to think about Newton's first law, which is that things in motion will stay in motion. So if I have this pulley and suppose there's no friction on it whatsoever, then that thing would keep on spinning until something did indeed act on it. We do know that it comes eventually to a stop because there is some friction on the wheel. So this bolt will stay put until something acts on it. So it should make sense right away that we would need some force acting on the wrench in order to get the bolt to accelerate. So rotation depends on the force. That's simple enough. Well, if I applied the force here on the wrench and the same sort of force, let's say that this might have been 10 newtons or something, at the head of the wrench, well, we would know that this would be more effective in turning the bolt. So there must be some dependency then on how far away the force is applied to the axis of rotation. The axis of rotation being the plane, the line that's coming out of the page here. So the farther away the force is from that axis, the greater the acceleration of this bolt. So let's consider that final position, or the position farthest away. And let's apply the same force, now just in different directions. So now I'll take my F and push it this way, and let's suppose that I push with the same force going that way, and that's also F. That's F. What will this force do? Well, it's going to do nothing. It's not going to accelerate this bolt. This one probably will accelerate it, but not nearly as much as the force that's perpendicular to what I've defined to be R. So it follows then that the angle of the force must also have some influence on how things are angularly accelerated. And if we look at the case where there's the most acceleration, that's where F is perpendicular to R. Now that's perpendicular. And if I was to consider, let me just for a moment keep this here, this F, then I would be interested in that angle there. But I'm really only concerned with the perpendicular component of the force. So the perpendicular component would be, I need another color for this. I'm going to break this thing up into an X and Y. It would look something like that. That would be my Fx. That would be my Fy. And that would be the component that actually makes a difference in accelerating this bolt. This component that's parallel with R does nothing. So writing this out in expression form, F perpendicular to R is what people call a torque. F perpendicular to R is a torque. You might also see this as F times R sine of theta, where theta is the angle between F and R. The units for torque are Newton meter. The first unit that we tackled in dynamics was balanced forces particle model. And that the premise of the unit was that if the sum of the forces is 0, so if the net force is 0, then there's no acceleration. net force is 0, no acceleration. There's a lot of parallels between linear motion and rotational motion, and the parallel here is that if I take all of the torques and add them up, and they equal 0, then there's no angular acceleration. So there would be no rotation. In this case, if this is the only force being applied to the bolt, there is absolutely a torque. That sum of all torques would be Fr, assuming this is a 90-degree angle. So I cannot say that the forces would be balanced, and I would predict that the bolt were to accelerate. Let's take a look at the direction of the torque, because the torque is a vector itself. So it's going to have a direction, and that direction isn't necessarily intuitive. Can you see that? I think you can. To talk about the direction of the torque, I'm going to use the example of a balance. And there I've got a balance. I've got two different weights on this balance. I've got mass big M and mass M over 3. Smaller mass is further away from the fulcrum. And I give you that this is balanced. So there's no angular acceleration, or another way of saying that is that the sum of the torques is equal to 0 if I have a balanced situation. No rotation. No rotation. So I'm going to look at each force that's acting on my balance and then come up with a torque that causes. So on mass A, which is the one on the left, I have a force due to gravity, Fg, which is big M, mass M, times little g. So the torque here, which I'll call torque A, is the force, mg, times the distance away, Ra, times the sine of the angle between them. Well, the sine of the angle, the angle is 90 degrees, so the sine of 90 is 1. Sine of 90. So this is mg_Ra. Remember, the torque equation is F. The perpendicular of R, which is also written Fr sine theta. To get the direction, we're going to use the right-hand rule. This is a new skill that I'm introducing here. There are 3 steps to this. 1, point your fingers in the direction of R. So for this torque, my R is going that way. 2, curl your fingers in the direction of the force. My force is going down, so I curl my fingers down. Finally, 3, you look at the direction of your thumb. That is the direction of the torque. So the torque is coming out of the page. Torque is out of the page. And I'm going to define that to be positive. So this is a positive mg_Ra. The next force that I have acting on this system would be from this mass. Fg is the mass, which is m over 3, times little g. So if I'm solving for the torque, then the torque of B, I have my force, m over 3 times g, times the radius away from the axis of rotation, RB. Okay. Times the sine of the angle between them. That angle is 90, so sine of 90 degrees, well, that's just 1. So now I do my right-hand rule again to try and determine direction. Fingers in the direction of R, and then I curl my fingers towards F. My thumb is pointed into the page, and if I define out of the page to be positive, then into the page must be negative. torque is into the page, that must be negative, so this value must be negative. So now I add them all up because I know that the sum of the torques is 0. So here I go, I'm taking all of my torques, which is 2, and I'm just going to put them in one expression. So mg RA from my torque A plus this torque, but this is a negative sign, so I'm just going to subtract m over 3g RB. Those are my two torques. I set them equal to 0. Now I could do a number of things in this situation, but maybe I want to find out the distance of RB in terms of RA. So I'm going to move this term over to the other side by adding it. So I get m over 3g RB. Oh, look, there's an m in every term. There's a little g in every term. And now I have RA is equal to RB over 3. Multiply both sides by 3. And in order to get an expression for RB, which says that RB must be 3 times the distance of RA. And hopefully you can make intuitive sense of that. If this mass is going to be 3 times, or a third of this mass, then it has to be 3 times as far away. So that's a simple balance problem to get you guys introduced with the idea of torque. More to come soon.